All right, lecture today is California geology. And before I get into the slideshows, I want to show actually 6 steps that it took for California to get to where it is today. So first, number 1 is up here, Pangaea is together. 250 million years ago, one big supercontinent at the end of the Paleozoic. Pangaea was a supercontinent from mid-Paleozoic all the way up until the mid part of the Mesozoic, and about 200 million years ago, this is when Pangaea starts to break apart. So here's a great big supercontinent, Pangaea. This included North America, South America, Africa, Europe, Asia, all one big super happy continent. Out here in the Pacific Ocean, there was a little bit of activity going on. There was a plate boundary that is going to be the future Farallon plate. And then something really interesting happens about 200 million years ago. A rift starts to occur right smack in the middle of Pangaea. So this is Pangaea before the rift, this is it during the rift. And at this point in time, convection is occurring. A string of volcanoes occurs from basically all up and down Pangaea, this big chain of volcanoes. These volcanoes are forming along a rift valley. So what happens at this point, North America starts going towards the west, and all of Europe, Africa, goes towards the east. And as time goes on, there's a lot of volcanic activity. This killed the early dinosaurs. So the early dinosaurs were tetrapods, very small reptilian dinosaurs. They were wiped out in this entire event because Earth was not a nice place to live at all. And then as the Atlantic Ocean grew basically, as North America went to the west, Europe goes to the east. In stage 2 here, the Atlantic Ocean is going to open up. Eventually these volcanoes are going to erupt underwater. And therefore all the volatiles, the CO2, the sulfate emissions, the ash, all of the nasty things that are associated with the volcanoes is going to disappear. It's going to get swept under the rug. And it's going to be underneath the Atlantic Ocean. It's still occurring today. Those volcanoes are still erupting today. Then we get down to stage 3 here. So now, as Pangaea breaks apart, North America is heading west. There's this oceanic plate out here, which we now call the Farallon plate. Here it is in its early stages. Now the Farallon plate is moving towards the east. The North America continent is moving towards the west. And the Farallon plate's kind of it's a problem child as far as plates are concerned. At the early part of the semester, I told you there's 2 types of plates. There's oceanic plates and there's continental plates. Well, as it turns out, the Farallon plate's a little bit of both. It's schizophrenic. It doesn't know what it wants to be. Part of it's oceanic, part of it's continental. So this plate is going to the east. North America is moving to the west because the Atlantic Ocean's opening up, pushing everything. And then this heavier plate is going to subduct, it's going to melt. The continents that it's carrying, so it's got little microcontinents on it. These little microcontinents can't subduct, so they stick themselves onto the North America continent. So in this part here, the boundary right here is Nevada. There is no California. California is going to be made up of all these little microplates that are going to stick themselves on the North American continent. This is what California is. So our terrain here, our geology is exotic. It doesn't belong to California. It came from a microcontinent called Rhodia. And Rhodia was a piece that broke off from Australia and Antarctica, which was in part of Gondwanaland. So first, Gondwanaland consisted of, so when this occurs here, when North America separates from Africa and from Europe, there's 2 continents that occurred, 2 supercontinents. One is called Laurasia, which consists of North America, Europe, and Asia. And the other one was called Gondwanaland, which was South America, Africa, Australia, Antarctica. And then a part of that broke away. Part of Gondwana broke away and they called it Rhodia. Rhodia came along with the Farallon plate and stuck itself onto the North American continent, which today is California, and parts of Nevada too. And so all of this continent collision results in the uplift of mountain ranges, and California geology is very complex. So here we are out here at the spreading center. There's convection going on here, where new material is being added. So this is new materials being added. There's convection. And as this new material adds, it pushes this Farallon plate to the east. The Pacific plate is being pushed basically to the west. And all these little microcontinents are going to be, it's going to be like a conveyor belt. Or imagine if you were in an escalator and there was a very big continent that was at the very front. Very big person gets on the escalator, and just small little people get on the escalator behind them. When that person gets to the top of the second floor, they don't step off the escalator. They just stand there. And that's when everything behind them is going to plow into them. And this is what the Farallon plate was acting like. So this is what the Farallon plate looks like during the good part of the Mesozoic, throughout the Jurassic, throughout the Cretaceous. And then this process continues until about 27 million years ago, when, let's turn this around, the North American continent is going to override that spreading center out there. Make sure I've got this in the proper focus perspective here. I have to check the camera. Yes, that's okay. So basically what occurs is, now we have the Mid-Atlantic Ridge. It's actively growing the Atlantic Ocean, but it's pushing North America to the west. The Farallon plate is getting smaller. All these little microcontinents, this used to be Nevada, this used to be the boundary. And now all this land is being added, which is going to be the future state of California. As this Farallon plate subducts, it melts. It creates great big magma bodies. These magma bodies were formed during the Jurassic and the Cretaceous, so throughout the mid to latter part of the Mesozoic. And these magma bodies are going to cool underground, they're going to crystallize, and eventually become uplifted, and they're going to form the Sierra Nevada mountains of today. So what was actually going on the surface here, and I looked this off, was there was a bunch of volcanoes going off here. These volcanoes have since then eroded away, they're gone. And what we have today is the Sierra Nevada mountains are basically the magma chamber that fed the volcanoes during the Mesozoic that is now cooled underground, millions of years later, and then uplifted. And then what happens is the North American continent is going to consume all the Farallon plate. It's going to go underneath North America. North America is going to make contact with the East Pacific Rise. That happens about 27 million years ago. And that is when the San Andreas Fault is born. And so our San Andreas Fault in California is a boundary between the Pacific Plate and the North American plates. So this is the Pacific Plate here. So this is the Pacific Plate. This is the East Pacific Rise, where new magma is being added. That magma is pushing the old crust aside. And then 27 million years ago, the North American continent makes contact with North American continent, makes contact with this East Pacific Rise. And this is the birth of the San Andreas Fault. And now that San Andreas Fault is migrating to the east. So the San Andreas Fault, as the North American continent continues to move to the west, that is overriding this spreading center. And so back 27 million years ago, the San Andreas Fault was right along the coast of California. It was right along the coast. Now it's inland. It's in the between the San Bernardino Mountains and the San Jacinto Mountains. And so the future is that the San Andreas Fault is going to migrate towards the east. And so this is kind of an overview of the history of the San Andreas Fault. And I'll actually use this drawing report here because it's much nicer if I need to draw anything else. Do a camera check here, make sure that we're looking at the PowerPoint presentation. Okay. All right. Cool. California geology. Well, here we go. So, we call these continental margins. California has had 4 different continental margins or plate boundaries. 4 different ones. The Atlantic type is what we see on the eastern seaboard of the United States today. It's called a passive margin because nothing's going on. Plates aren't converging, they're not moving away from one another. Basically, the eastern seaboard of the United States is passive. Nothing's going on tectonically there. We've had times when we had subduction zones going towards the west and subduction going towards the east along California. And then we had continents slamming into one another. We had continent to continental. And then today, we have a transform plate boundary. So California has seen practically every type of plate boundary. Ocean to continent collision, continent to continent, ocean subducting to the opposite direction, and this resulted in very unique geology in California. So this is a diagram that kind of shows these. The Atlantic type is what we see at the top, very passive margin, tectonically nothing's really going on there. And then we had subduction, where Farallon plate subducts and goes underneath the North American continent, it melts, it creates a chain of volcanoes on the surface. Underneath is this igneous rock forming. An island arc is basically because, like I said, the Farallon plate was a confusing plate. Here's a piece of oceanic material that made up the Farallon plate. This is a continental piece, another ocean plate. So this ocean plate subducts and goes underneath and creates a little island chain off the coast of California, which is kind of the way we see today in Japan, so, which is why they call it the Japanese type. And then the California type is where the North American continent has overridden this spreading center, and this spreading center is now underneath, kind of swept under the rug, and it's become our San Andreas Fault. So the California type is transform fault. No subduction, because the Farallon plate is off, it went bye-bye, it's gone, it's underneath us. It's probably actually underneath Nevada and Utah, still melting. So the age difference in the rocks is what threw geologists off. So before the geologists really understand this whole thing about continental drift, and we've gone to the Mojave Desert. So I've led field trips, my students, and we look at rocks that are 510 million years old. And then right next to it, there's a rock formation that's 1.7 billion years old. That's a huge time difference. And these very old rocks are a rock called Rebekivi granite. We'll never see Rebekivi granites form on Earth again, never, because Rebekivi granites formed at a time when Earth's crust was extremely thin. And they had these zone plagioclase, which are really cool. And we find this granite throughout California. There's a bunch near Baker, California. There's a bunch of along I-40 between Ludlow and Barstow. And so this rock came from Australia. So we have pieces of Australia way in deep in California. There's some stromatolites, which are these algae fossils that are 1.3 billion years old that were formed from Australia. And they're at the border of Nevada and California. So California basically is kind of a collage of a bunch of little continental material. And so you go from one mountain range to the next, completely different rocks. And that's why the Mojave Desert is really unique geologically. So the oldest rock is this Rebekivi granite. We find this in the deserts located out throughout the Mojave Desert, California. It's a porphyritic rock. It's pretty uncommon. You don't find a lot of it. In fact, I discovered some out when I was an undergraduate, when I had transferred to UNLV. When I gotten into the UNLV Geoscience department, I was out in the desert just exploring, and I found this really weird rock, and I took it to an igneous petrologist, and he was from Wisconsin, and his eyes almost came out of his head. He goes, whoa, 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 where did you find this? You know, I go, well, I'm in the desert out here in these hills. So I took him out there and showed him, and he was just amazed, and he goes, he told me all about the history, and I kind of worked on some thin sections and worked on a project with him on this. And it's really a neat rock. And so today we find this in parts of South America. It's called part of the Baltic Shield, which really goes up into the northern part of what is today Russia. It extends over into Greenland and even into Canada. So we find this very old rock, part of Gondwanaland. Gondwanaland then broke up from the little microcontinent called Rhodia. And so this is kind of the little microcontinents that came in. And this is basically what the North American continent looked like 1.7 billion years ago. So this is coastal California right here. So this is our coastline, the San Francisco Bay. Notice we're just all ocean. This would actually be Las Vegas, Nevada, maybe St. George, Utah right there. And you can see there's an ocean in between. So at this time, North America is a highland to the west, and then over to the east coast, there's the Appalachian Mountains. And this is that Rabikibi granite. Not a very good picture of it. And so if you look at a geological map of the United States, you can see that a lot of these rocks go across vast areas. This is the blue area in here. These rocks are based on ages. So Paleozoic rocks are generally in these blue color rocks. Precambrian rocks are in red. And then very young rocks are in greens and yellows. And notice that there's a lot of green and yellow in California because we're a young continent. We came from other places, but scattered throughout are these little red patterns. And we find these in Nevada and Arizona. These are these old Precambrian rocks that came from Rhodia, that little microcontinent, part of that Precambrian shield. So passive margin, throughout the Cambrian, it was a very passive margin. It was great if you were a marine organism. You would have loved to live off the coast of Nevada in the western United States then, because perfect waters, they were tropical, not a lot of sediment, there weren't any mountain building events. So coral reefs and marine aquatic organisms that are filter feeders don't like a lot of sediment in their water. They don't want things mixed up because they're filter feeders, and sand has a tendency to clog those filters. And so it's a very great place, and this is why we find trilobites just flourish at this time. So this light blue color is very shallow, what we call epicontinental seas. So this is very shallow water. The darker blue out here is deeper water. And so this area, this is where the trilobites lived, in the brachiopods in the early Cambrian. This area just was the perfect environment. At this time, the North American continent is right down at the equator. So it's very warm, tropical waters, shallow, huge continental shelf. And that was basically the passive continental margin of early California. So this is why we see a lot of trilobite fossils. You can go to the White Mountains of California and you'll find these trilobite fossils. You find them at the end of Marble Mountain. There's still a section that hasn't been metamorphosed, where you find trilobites like Olanellus clarkii, which is indicative of Upper Cambrian rocks. And so we find an awful lot of trilobites and rocks around California and Nevada because this is the place they love to live. There's a really tight locality right near Nevada, Las Vegas actually, that you find the Olanellus clarkii clan, those three different Olanellus trilobites. So then Mesozoic is going to mix things up, because when Pangaea starts to break apart, the stability of the western United States, as far as being a passive margin, now is going to be an environment where plates are coming together. These plates are going to cause continents to uplift. They're going to cause massive erosion, and it's not going to be good for marine organisms at all. So the western North American continent starts to move west against eastward moving oceanic crust. This is the Farallon plate. And due to these continental rocks weathering and eroding, they're shedding a bunch of sediments out into the ocean. This is choking up in marine organisms. This actually led to a couple of extinctions in the early Paleozoic. When continents start moving, it actually results in extinction. A lot of deposits of shale and conglomerates. These shells or conglomerates are going to later then be pushed back onto the continents again. On the field trip up to the Santa Ana Mountains, there's all those pelagic sediments that form off the coast, which we now find in the Santa Ana Mountains. They were formed in these types of environments. So as these continents are eroding, they're shedding sediments into the Pacific Ocean, and then when those continents start to collide, it's going to take all that sediment and push it onto the continent, forming today what we know as the Santa Ana Mountains. So here is this Gondwana land piece that break off from Australia and Antarctica. We call this Rhodia. It wasn't one continent, it was actually a series of continents. There's a mountain range in Northern California called the Klamath, and we can recognize 4 different little microcontinents just in the Klamath Mountains alone. There's a lot of areas here in the southwestern United States that really haven't been studied, and we need geology students to go out and do master's and PhD studies and get a handle on what was going on with these rocks. This is an interesting group. These are what's called the Pahrump group. Today, these rocks which were in California, are now way up here. So notice there's mixed up sediments, so this area really gets mixed up. And you have to realize that when these continents, so all this stuff is moving towards the west, towards the east, as the North American continent moves towards the west, continent-to-continent collision, and then wham, you start to see mountains uplifting, and it's not a very good time for marine organisms to live because they don't like stirred up waters. They don't like a lot of sediment being discharged into those bodies of water. So this is a cartoon showing basically this eastward subduction, that we had a plate that was, here comes that Farallon plate with its little microcontinents, and some of the ocean plates are going to subduct towards the west, and some are going to subduct towards the east. So the direction of movement is from the east, so it hits this little microcontinent, it subducts, creates a little island arc, kind of like what Japan is today, and then later this island arc is going to be pushed onto the back onto the North American continent. So this is why California geology is really complex. So we have all these different orogenic events. We have the Nevada, we have the Severe, we have the Antler. These are different mountain building events. So we have recognized 4 major mountain building events from the Mesozoic to about 27 million years ago. That's a lot in that span of time. Appalachian Mountains were formed basically in 2 orogenic events. So we see right lateral fault, where today we see the absolute opposite. And this is really good evidence that California grew from the east towards the west. And it's all because of this accretionary tectonics. So here's another picture. So what we call this term, when continental material gets slammed onto another continent, and all this sediment in between, what's going to happen to all this sediment in between here? It's going to be pushed on. And that's exactly what the Santa Ana Mountains, the foothills, are of today. They're basically a bunch of sediments that form the oceans that were pushed up into the hills that we see today. Now it's all eroding and trying to come back out to the ocean again. That's just the way nature does things. Very complex geology. So here, this kind of shows, as this Farallon plate starts to duct, all this eroded material from rivers is supplying sediment. It's depositing this sediment off the coast. And this conveyor belt is picking these sediments up and just plastering back onto the North American continent. And so those green sediments and those red sediments on the Santa Ana field trip that I videoed this year, unfortunately, we generally visit that locality, but because of conditions the way they are, it is what it is, and we have to do video field trips instead. Strange, isn't it? Just like we're doing video lectures. I wonder if anybody's watching. So the funny thing about this is that California is a bunch of little teeny subplatelets. And when you go to the Santa Ana Mountains, you see those red rocks and those green rocks. Some of those are formed in deeper water, and some of them are formed in shallower waters. And this is why you see this very huge array of rocks. So this is just another diagram showing this would be the rock that we see today in San Diego. All this material is being eroded. This is like the Torrey Pines Formation along coastal San Diego County. And so as this Farallon plate is moving to the east and the North American continent is moving to the west, all this material is going to get sandwiched in and accreted onto the North American continent. And we call this accretionary tectonics. So accretionary tectonics, accretionary was part of the supercontinent Rhodia. It was definitely a part of Antarctica in Australia. So when Gondwanaland formed, a small continent broke away from Gondwanaland, which is basically Antarctica, Australia, and India. India broke off and went all the way across the equator and went to the northern hemisphere. It's probably the poster child. It was probably the most active little plate of all the plates. Moved the most. And then Antarctica and Australia are eventually going to rip apart. This is going to break up this little continent. We then have a little microcontinent that comes out of this called Rhodia, and Rhodia is going to come over and join California. And that's kind of the history of that whole thing. So this eastward subduction of the Farallon plate is because, like I said, the Farallon plate was a plate that consisted of a whole bunch of different plates. Some continental material, some oceanic material. And Colluded within is all the material that's being eroded off of the North American continent. So here's the Farallon plate. It's subducting, it's going underneath. Eroded material is coming off the volcanoes that are the future Sierra Nevada mountains are being formed down here. This magma body is going to crystallize. It's going to form granite. And then that granite is then going to be uplifted because of continent-to-continent collision. A lot of material is being eroded. So today we see this process. Africa gets these huge dust storms, huge windstorms come across the African continent to the Sahara Desert. They pick up all that sand, and then when those storms go out in the middle of the Atlantic Ocean, they kind of break apart. And as they do, they lose their velocity, they lose their wind speed, and all the sediment that they were carrying drops into the Atlantic Ocean. They think the same thing was occurring in the Pacific Ocean. There are some sandstone formations in the Santa Ana Mountains and down in San Diego that were probably formed this way. So one of the things that geologists do is we look at processes that are occurring today, and we try and extrapolate from that this is how these rocks that we see in San Diego and the Santa Ana Mountains today were formed by the process that we see going on today off the coast of Africa in the Atlantic Ocean. So this is actually in the Klamath Mountains. And there are, like I said, there's all these different belts, and these are easily recognized belts that came from that microcontinent Rhodia. And so there's really good proof that California is basically a collage of a bunch of small little microcontinents that basically were pushed together. And don't worry about some of these opalite terminologies. It's just a different type of a rock that occurs when continents kind of suture themselves together. Catalina Island is a really good example of a microcontinent that came from Rhodia. It's basically part of Australia. Some geologists believe that it was on the North American continent and it was later rifted away by the San Andreas Fault. But Catalina Island is unique because it doesn't fit the geological profile of California. The geology of Catalina Island is unique. If you look at the other Channel Islands, and that chain of islands out there, Catalina Island is unique. It has green schist and blue schist rocks. These rocks are indicative of a continent that tried to subduct, and it might have subducted. It might have got buried in some sediments that were eroding off the continent, and then it popped back up. And that's why we find green schist and blue schist in Catalina Island. So Catalina Island is one of these real keys. So if you look at like the Santa Cruz Islands, they're completely different geologically. The rocks don't match the geology of Catalina Island. So Catalina Island is unique. It's part of what we call a Franciscan complex. It has blue schist, and these little red things are garnets. These are not gem quality garnets, they're just very crude garnets. But this rock tells us that this was kind of formed at some depth and some pressure. So that kind of lets us to believe that Catalina Island really tried to subduct, but because its continental material was too light, and then popped back up. So we see this whole sequence of rock. We see amphibolites, we see green schist and blue schist, lots of shells. And so like I said, the geology of Catalina Island is very unique. It's something that has been formed at depth along the subduction zone. It probably was, and then for some reason it popped back up. I think I read a professional paper where the author had described it kind of like a cork popping back out of water. And that's what Catalina did. So these are some of the other rocks. Don't worry about glaucophane. It's a mineral that is associated with subduction, with the blue schist and the green schist phases of metamorphism. So what's happening? This is what we see today in the Santa Ana Mountains. We see these sequences where we find shells and conglomerates, and this repeated layer where you'll see a shell, conglomerate, shell, conglomerate, shell, conglomerate. And the theory behind this was that erosion is taking place, and all this material is being deposited out in the ocean, and then later it's going to be pushed back onto the continent by these continents coming together. And this is what I videoed in the Santa Ana Tucker Wildlife video. We saw some sediments that were red in color. Red in color is indicative of shallow marine environment where there's plenty of oxygen to oxidize the iron. The green color rocks that were so above the red rocks, those are basically, they tell the story that those rocks were formed in an oxygen deficient environment. So that's what we call oxygen, iron reduction, the lack of oxygen. And that's why we find these green rocks. And those green rocks are a really good hint, especially with all the jasper and the flint that's in those rocks. That tells us they were formed in deep water and then pushed up into the hills of the Santa Ana Mountains today. So this is where your Santa Ana Mountain hills were formed, right here. Now, they're away from the mountains, and you have to go up in elevation to see those. So as that Farallon plate subducts that East Pacific rise, eventually this North American continent is going to override this. 27 million years ago it did that, and that's when the San Andreas Fault was born. So as this Farallon plate subducts, it's melting, it's taking all these metamorphic, all these sedimentary rocks, right? With it, these shells are going to be drugged down and they're going to form slates. You're going to drag the slate down, it's going to form a phyllite. Take the phyllite deeper, it's going to form the schist. The schist is then going to form a gneiss. The gneiss is going to melt, it's going to form magma. When it crystallizes, it's going to become an igneous rock. So this is the ancestral Sierra Nevada mountains. So uplifting the mountain ranges, San Gabriel Mountains uplift because we have these continents are colliding. So as things collide, they push up. And this is when the San Bernardino Mountains are formed, the Santa Monica Mountains, San Gabriel Mountains, Santa Ana Mountains, and even, yes, the Sierra Nevada Mountains. So all the coastal ranges are born at this time. And this is the topography we have today. So this would be the San Fernando Valley, then you have the LA Basin, the Antelope Valley, which is upward Lancaster, and here is the San Gabriel Mountains. The San Gabriel Mountains currently are the second fastest growing mountain range in the world today. The fastest growing mountain range is the Himalayan mountains due to the Indian continent slamming into the Asian continent, uplifting. Same thing happened here. The reason that these mountains are growing because the San Andreas Fault is kind of twisting through here. It's kind of dragging these rocks along, and there's some resistance here, so the resistance is resulting in the energy being pushed upward. And so the San Gabriel Mountains is the second fastest growing uplifting mountain range in the world today because of the San Andreas Fault. So this basically shows a time lapse that I kind of drew on that, where it shows here we have the Pacific plate out here and the Farallon plate. And then the North American continent is going to override and touch that. We think the initial point of contact with the Farallon plate was also subducted, and its spreading center made contact was right near Los Angeles, ironically. And then as time goes on, the San Andreas Fault is growing because that spreading center is being pushed underneath the North American continent as the North American continent overrides it. And today, that spreading center is basically taken the Baja Peninsula of Mexico. It has sheared it, ripped it away from the mainland of Mexico, and it goes right up the Sea of Cortez. And now the San Andreas Fault is east of Los Angeles. As the North American continent continues to move to the west, the San Andreas Fault is going to move toward the east. It's trying to hook up with some faults right now in Barstow, like the Calico Fault. And that area, I think, is going to see a lot more seismic activity. Ridgecrest is probably a good example of that. The earthquake that occurred July 4th of 2019 in Ridgecrest is a result of the San Andreas Fault moving towards the east. So LA Basin, it has a lot of geological potential for earthquakes because in the background are the San Gabriel Mountains, the second fastest uplifting mountain in the world today. That has a huge potential to create or generate a large magnitude earthquake. So here's that diagram. I love this sort. So here's the North, so really the North American continent is moving west. And there goes the Farallon plate. It goes bye-bye. It goes underneath. And then as the San Andreas Fault now starts to activate, it starts to stretch the North American continent. I mean, look what happens to Nevada. Look what happens to California. As that San Andreas Fault starts to stretch the continent, it's going to rip Baja away from the mainland of Mexico. So Baja gets ripped away. And so what's the future? San Andreas Fault is going to continue to move to the east. It's going to link up with Barstow Faults, the Calico Fault, and then eventually it's going to make itself go right through Death Valley. And I think we're going to see an increase in seismic activity in eastern California, Death Valley, and those areas. So Ridgecrest is probably just a prelude of what we're going to see with respect to earthquakes. So because the continent is being stretched, we get these flood basalts. The San Andreas Fault is stretching the continent, it's also thinning the crust. And so as that crust becomes thin, it allows magma to penetrate and to form volcanoes. So the North American continent over at the Spring Center, so the San Andreas Fault is what used to be the East Pacific Rise, the Spring Center. That Spring Center is now underneath the North American continent. And we call that the San Andreas Fault. And that plate boundary is a boundary between the Pacific Plate and the North American Plate. So in Southern California here, we live on the Pacific Plate. When you go through Cajon Pass and you go up towards Victorville, you go onto the North American Plate. So Barstow, Victorville, they're all on the North American Plate. As you go down Cajon Pass into San Bernardino, that's all the Pacific Plate. So we live on the Pacific Plate. The Pacific Plate is moving to the north and to the west. The North American Plate, where Barstow and the rest of the United States and Wisconsin and New York, is all moving directly towards the west. So because the land is being pulled apart, it's creating what we call a basin and range topography. This is extensional tectonics, and these valleys are being formed by normal faults. So remember, a normal fault is a block of rock that moves down. And that's how the basins, such as Death Valley, were formed, and they're still being formed today. Death Valley is still downdropping. It's 283 below sea level. Come back in another 10,000 years and it might be 295 feet below sea level or something like that. So interesting thing is as these plates start to collide, it takes the center part of California, which we call today the San Joaquin Valley, and it creates a big valley. So we have coastal rocks, and then we have the Sierra Nevada mountains. And what's stuck in between? Fresno, Sacramento, Bakersfield. That is what we call the San Joaquin Valley. Great big long valley going up through California. And that's kind of a compressional wedge that occurs as these mountains are uplifted and compressed. The San Joaquin Valley in the middle kind of folds downward, forms a great big syncline. And some of those synclines, so there's actually an anticline right where the San Andreas Fault is. And then there is this syncline. That's where we find oil along the San Andreas Fault in Bakersfield. And so if you look at, this is a map showing California. This is Baja. Here's the coast of California, San Diego, Los Angeles, Palo Verde Peninsula, Newport News Fault. Look at all the faults here. We have the San Clemente Fault. San Diego Trough, which actually connects down here with the Agua Sierra Fault. We have the Palo Verde Fault. We have the Newport Inglewood Fault, the Elsinore Fault, the San Jacinto Fault, the Banning Fault, and then of course the San Andreas Fault. So California has a lot of faults because it's being stretched. And as it's stretched, it's breaking apart. It has this brittleness to it, and that's why these rocks are forming these nice little faults. So this is actually in the Bay Area. So in the Bay Area, you have the Hayward Fault, you have the San Andreas Fault, you have the Green Valley Fault, and any of these faults can basically move, generate an earthquake. So in 1906, when modern society experienced its first major earthquake, it was in 1906 in San Francisco, and that was along the San Andreas Fault. This is part that moved, and it moved between 6 and 8 feet in about 15 seconds, which generated a very large magnitude earthquake that actually destroyed the entire city of San Francisco. It'll probably happen again. And a lot of seismologists predict that every 100 years, San Francisco should have a major earthquake. And the last one occurred in 1906, and so they're slightly overdue. So here's a satellite image showing the San Andreas Fault. So you realize that everything that's on this side of the San Andreas Fault is on the Pacific Plate. It's all moving towards the north and to the west. And everything that's east of the San Andreas Fault is moving to the west, and this is on the North American Plate. So North American Plate, Pacific Plate. Two different plates. Side-by-side motion, San Andreas Fault. So because of this essential tectonics, the Imperial Valley has been downdropped, Death Valley, and right now the Imperial Valley is below sea level. And as the Imperial Valley drops, it's stretching. There's a lot of obsidian, so I did that little field trip where I videoed the volcanic rocks at the lower end of the Salton Sea. You'll see rocks like obsidian and pumice down there. And that's indicative of a pretty explosive volcanic eruption. And as that crust continues to thin, there will be future volcanic eruptions out in that region. So this is a satellite image showing, here's the California-Mexico border. This is the Salton Sea, and these are the agricultural fields. This picture is not coming out very good. Here basically is that same aerial photograph with the San Andreas Fault. So today, up north, Northern California, Oregon, Washington, British Columbia. Their tectonic setting is where California used to be during the Mesozoic and the early part of the Paleozoic. So up until about 27 million years ago, we had active subduction. Plates were melting, subducting, creating volcanoes. So if you were living in Southern California throughout the latter part of the Mesozoic, throughout the Jurassic and the Cretaceous, and in the early part of the Cenozoic, you'd have experienced a lot of volcanoes. There was a whole chain of volcanoes, and we have some of those remnants of those volcanoes in the Santa Ana Mountains. Today, we find shale, sandstones, and shale sequence, some conglomerates. This is typical what we see in coastal California. So most of the coastline of California is a sea cliff. And the reason we're a sea cliff is because we've been pushed upwards. If you go to the Asian United States, they have broad continental shelves, a huge continental plain that extends out in the ocean. We don't have a continental plain that extends out in the ocean. We don't have a continental shelf. It's because our coastline is dominated by recently uplifted rocks, and we get this very cliffy environment. So along the coast of California, you find basically cliffs. So what's going on right now? As the North American continent continues to move west, the San Andreas Fault is going to grow to the north. So eventually that San Andreas Fault is going to continue because that Juan de Fuca plate, it's now a remnant plate, which they call, there's actually three little subplates they broke it up into. And the Juan de Fuca plate is basically a remnant of the old Farallon plate. It lies off the coast of Northern California, Washington and Oregon, or Oregon and Washington, and British Columbia. California is going to continue to tear apart as the land stretches. So sediments from the Pacific Ocean have been pushed up onto the North American continent. This is what we saw on the field trip, on that video field trip. And this basically shows the current situation that's occurring in Northern California. So Mount Lassen, Mount Shasta, these are active volcanoes because this is that remnant of the Farallon plate, which they broke up into three plates, the Gordia, the Juan de Fuca plate, and the Explorer plate. These plates are being subducted, so this is the spreading center. Eventually, Oregon, Washington, British Columbia are going to override these spreading centers, and this is going to make the San Andreas Fault move towards the north. So this is what California used to look like in the latter part of the Mesozoic. We had a chain of volcanoes. So today, in Northern California, Mount Lassen, Mount Shasta, McLaughlin, Crater, all the way up, you've got the Three Sisters, Jefferson Hood, you have Mount St. Helens, Mount Rainier, Glacier Peak, and then Mount Baker, and then up into British Columbia. You have this whole sequence, and this sequence of volcanoes continues all the way to Alaska. This is what California looked like. So what's underneath these volcanoes is a big magma body. And eventually, this magma body is going to uplift when this subduction stops. And the Sierra Nevada mountains are going to grow towards the north. Because the land is being stretched, it's becoming thinner. And thinner land allows magma to penetrate it. So this is a map showing all the volcanic activity between 5 and 10 million years ago, and between 0 and 5 million years ago. So these are all the hot spots for volcanic activity. That doesn't necessarily mean that volcanoes have surfaced, it means that they're near surface. A good example is in Southern California, there's a lot of hot springs. Those hot springs are associated with magma bodies that want to try and come up. And to realize that things in geology move over millions of years. If we live to be 100 years, that's a long time. But in geologic time, 100 years is nothing. So a lot of these magma bodies, they don't move overnight. So out in the deserts of the Mojave, there's Amboy Crater, last eruption about 10,000 years ago. So in our perspective, 10,000 years, that's like, wow, that's a long time. But in geologic time, 10,000 years is really nothing. These volcanoes have been erupting out in the Mojave Desert for the past 5 million years. So this is basically a May 1915 eruption of Mount Lassen. This predates Mount St. Helens by quite a few years, and this is like the first really continental volcanic eruption that occurred in the continental United States in recorded times, in history, historic times, an event that was very well recorded. This is a mountain that literally blew itself apart, much like Mount St. Helens. So you had a very high mountain range that in one catastrophic event blew itself apart. And then 1980, this is going to be repeated, but not at Mount Lassen, but at Mount St. Helens. And so off the coast of California, you see these peaks. These are old volcanoes that are now dormant or asleep. And of course, up and down the western United States, a whole chain of volcanoes. These volcanoes are occurring today because that remnant of that Farallon plate is subducting. It's going underneath the North American continent. That plate's melting, that magma bodies are coming up in the form of volcanoes. So Mount Lassen, you know, they formed Mount Pangaea, composite volcano, built about 1 million years ago. And then it collapsed, they don't know exactly when. And then a deucite formed, very mafic, iron-rich rocks formed about 11,000 years ago. And then they had some eruptions where the volcano literally blew itself apart between 1914 and 1921. And then after 1921, Mount Lassen basically stopped activity. And there was no volcanic activity. So from 1921 until May of 1980, the Pacific Northwest was without any volcanic eruptions whatsoever. And then Mount St. Helens erupted in 1980. Today, often near the ski resort of Mammoth, there are some volcanic rocks. There's a lot of seismic activity, a lot of small little earthquakes, and there's been some changes in some hot springs near Mammoth. And a lot of volcanologists, people who study volcanics, and igneous rock petrologists, feel that the next volcanic eruption in California will probably occur near Mammoth. They think it's getting ready, that magma bodies are beginning to move up. Although a few years ago, a magma body was moving up into Yellowstone, into what we call a supervolcano. And since then, that magma body has subsided and stopped rising. So these magma bodies, they might rise and then subside, rise again. Really hard to predict exactly when a volcano is going to erupt. But the last really time that there was a major volcanic eruption up along Mammoth, along the east side of the Sierra Nevada mountains, was about 30,000 years ago. In geologic times, 30,000 years, that's like last week. So Morro Rock is basically a center part of a volcano. It consists of porphyritic andesite. So this has been a very explosive volcano. Will Mortal Rock or the Seven Sisters or any of those volcanoes erupt again? Most likely not. Because the Farallon plate and the North American plate have moved to the point where that volcanic activity is being centered into the Mojave Desert, more east of the coastal area. So this is actually Amboy Crater. I had a field trip planned for Amboy Crater, but it was canceled. Amboy Crater erupted 10,000 years ago. This was a very mafic eruption. So this is what would have been a volcanic eruption, much like you see today in Hawaii. Native Americans probably witnessed this. It would have been a type of volcanic eruption that people could see without being blown away. It was not like Mount St. Helens, that it was rich in silica. This is a volcano rich in magma. The magma which was enriched with iron and magnesium. Those eruptions tend to be very mild, where the lava just kind of flows out. It's very fluid-like. The magma that's rich in silicates tend to be very viscous and sticky, and those rocks explode. So Amboy Crater, pretty neat lava flow. A lot of lava flows erupted from Amboy. They have some lava flows that extend out towards the west, and a huge flow that goes out to Bristol Lake. And I'm trying to get together maybe a field trip. We'll see what happens for the fall back out to Amboy Crater. Really neat crater. This is one of the rare craters where you can actually hike down into the crater of a volcano that last erupted about 10,000 years ago. So, current geology. We have uplifting mountains that are still uplifting. They've uplifted for years. We still have coastal sediments that are eroding and going off into the ocean. We have very unstable cliff facies, which makes the western edge of California extremely vulnerable to landslides. Could we see volcanic activity? We will. If we'll see it or not in our lifetime, it's hard to say. But California will see some more volcanic activity in geologic times. The last ice age ended about 12,000 years ago, 12,800 years ago, to be more precise. That's when global warming really starts, about 12,800 years ago. So last ice age ended about 12,000 years ago. And what those glaciers did is they took the Sierra Nevada mountains, the Rocky Mountains. Those mountains were twice the elevation that they are today. They have been basically cut down and eroded by the weathering of glaciers. So this is a good example of mechanical erosion, where heavy ice acts like sandpaper carving out the rock. So here are the Sierra Nevada mountains and the Rocky Mountains. This profile fits both. Those mountain ranges were twice as high as they are today. They've been cut down by 5 major glaciation periods. And so ice is very heavy, it's very dense, it's very erosive. It's like sandpaper. So El Capitan and Yosemite. So if we were in Yosemite here 10,000 years ago, there would have been no trees here. This would have been occupied by a glacier. So about 12,000 years ago, the ice started retreating, climate started warming, humans started taking over. So you look at the human population, it can be basically correlated with the end of the last glaciation. That's when humans really dominate the world. As the earth warmed, we took it over. And so this rock is very hard. It's granitic rock. This was formed when the Farallon plate subducted, melted. That melted material then crystallized in the ground into what we call crystalline rocks. These are granites. And now this rock has been uplifted. After it was uplifted, it was subject to erosion, carving out by granitic rocks. So this is what nature does. Uplifts mountain ranges and then creates glaciers that tear them back down again. And this is the ongoing cycle of geology. The rocks are polished in some places. Big gouges are left in them. So this is why geology is always known about the glaciers and that the ice ages occurred. As I talked about earlier, the Midwest United States, so areas like Nebraska, Ohio, Kansas, they have very good farm soils because glaciers which started in Canada moved to the south. And as they moved to the south, they carried with it crushed granitic rock. So inside granitic rocks are minerals that are enriched with potassium, iron, magnesium. And those are essential for good soils. And so the good soils of the mid part of the United States can be attributed directly to glaciers that took crushed rock, granite, from Canada and acted like bulldozers and moved all that rock. And then when those glaciers melt, they leave all the rock behind. And they did this 5 different times. 4 major glaciations and a minor glaciation. So in California, we had a similar process going on. A lot of the good soils we see today in the San Joaquin Valley, between Bakersfield up to Sacramento, that was basically formed as a result of glaciers carving out the granitic rock in the Sierra Nevada mountains and then pushing that material into the valley, the San Joaquin Valley today. So what's the future? Continue moving along the San Andreas Fault system. So the San Andreas Fault is going to continue to move east. As it does, it's going to continue to stretch the North American continent. It's going to continue to make our crust thinner, which is going to make it more vulnerable to volcanic activity. So, very good possibility in the Mojave Desert, Amboy Crater, and some other craters out there could see some resurgence of activity. That's very possible. And that's a light screen because of Microsoft. And don't you just love technology when it doesn't work? I don't know why this does this every now and then. But we will, okay, why did it go all the way back to there? You guys are kidding. Okay, so it really threw us out of the system here. But we're almost done, so I guess we are done here. Okay, I guess I must have known that we're done with this particular segment here. Let me just kind of go over here. So they're going to be continued movement along the San Andreas Fault. And the San Andreas Fault is going to move to the east. What does that mean for places like Barstow? Certainly an increase in activity of earthquakes. You have to realize that the mountain ranges and the deserts were formed because of tectonic processes. And tectonic processes generate earthquakes. So if you live in a mountain area, you can expect to see earthquakes. I was looking at on a site where a guy had talked about this end of the world doom thing he was talking about. He said the coronavirus has started. It's the beginning. And he said, then he points out, well, there was earthquakes in Utah and Idaho. Well, yeah, Utah and Idaho are surrounded by mountain ranges. Those mountain ranges were uplifted due to earthquakes. So if you live in an area where there's mountains, you can expect to have earthquakes from time to time. It's part of the process. If you don't want to have earthquakes, move to Kansas. They don't have earthquakes there. They have no mountains. Of course, they have tornadoes. So definitely volcanic activity in Northern California. Mount Shasta could really see a resurgence of volcanic activity. I think most likely, according to what I've read in the press, in the academic press, is that we're going to see volcanic activity out in the Mojave Desert, or possibly Mammoth. I would probably put my money on the Mojave Valley, because that area is really being stretched more rapidly than along the Sierra Nevada mountains. So that ends California geology. And that's that.